Hi, this is part 4 of the series of lectures on systems identification and modeling. In this, we are going to see, to some extent, the benefit of the first 3 lectures because we are going to be doing our first modeling exercise. Since I'm keen on teaching the subject as well as the methodology, I have chosen a very simple exercise. We are going to be modeling a simple system. The beauty of the system is that you already know about it. It could be used to model just about any and every mechanical system that you may come across in real life. We will be doing the modeling by more than one method, and thereby we will be establishing what it means to actually say, let's model a system. The steps are very clearly outlined and demarcated. There is a flow chart at the end of the lecture that will show you how you can start doing modeling. So you could say this lecture is more in the nature of a template. We are not going to go into solution or response or system analysis at all. That is pure mathematics, and so it is reserved for a later session. First part, identify the applicable theory. What is it that we need to be thorough about so that we can handle what we have to do? Free body diagram approach and Lagrangian approach. These are two methods to establish, determine, derive what is known as equations of motion. We are going to be looking at a dynamic system, a body in motion. So to model such a system is to come up with the equations of motion. That is what modeling means. If you can derive the equations of motion, you can analyze the system of body or bodies so that you can tell about what they will do subject to a certain input. So the first method is to do a free body diagram. Why a free body diagram? Because with a free body diagram, you establish a balance of forces, externally applied forces. By taking the externally applied forces, you'll be able to find a resultant and its direction. The second method is the Lagrangian approach. The Euler-Lagrangian generalized equation gives you the condition of a system of body or bodies as a function of the Lagrangian. The Lagrangian is defined as L is equal to T minus V, where T is the kinetic energy and V is the potential energy. There are two other factors besides the energies caused by the motion. They are the dissipation of energy due to things like friction, drag, viscous damping, etc. And of course, the corresponding external loading, which always has to be provided for from outside the system of bodies. In general, the equation often reduces to, in the ideal circumstances, reduces to a system of equations where there is no energy dissipation. The next step is to define the problem, to look at the component parts. So far, we have looked at what theory we need to know, namely free body diagram and the Lagrangian. These can be looked up at any external reference. But now we are into defining a problem. Mostly in the engineering industry, particularly mechanical industry, we look at things like machine systems, like trusses, like systems with moving parts such as an automobile or a motorcycle or a pump or even a motor such as a ceiling fan, an air conditioner. All of these have certain fixed components. These components are usually very straightforward to model. In this case, we have taken a very simple case study because our intention is to demonstrate the methodology behind modeling a system. We are not here to get into the nitty-gritty of a particular area of study. So we will model the system, then study the system using two methods. One is the free body diagram and the other is the Lagrangian. All these systems typically contain four components. One is the inertial set of forces which are caused by the mass of the system. Second is the stiffness, that is the rigidity or the corresponding flexibility of the system. Third is the loss that is created by aerodynamics or by friction or by any other viscous damping. And the last, of course, is the system of external forces. So we can take this to be a spring mass damper system, which can be taken in the ideal sense to represent a majority of things we come across in real life. Having defined such a system, let's look at the component parts. To use the free body diagram method, we look at a spring mass damper system. We have the force, restoring force of the spring equal to Kx acting upwards. We have the damping also acting upwards, and we have the external forces applied. So given that downward direction is positive and we write the balance of external forces, you get mx double dot plus kx plus cx dot is equal to sum of external forces. The F indicated in the drawing is, of course, the resultant force. To do the Lagrangian method, we need to estimate the energy systems. One, kinetic energy, which is nothing more than 1/2 mv squared, where v is represented as the first derivative of displacement x. Second is the potential energy, 1/2 kx squared. R is the dissipative energy, Q is the external loading. So the Lagrangian is T minus V, defined easily that way, and the partial derivatives with respect to velocity and displacement are derived easily. The effect of dissipative energy in the system is given by the damping force. So to assemble the entire Lagrangian as given in slide 3, gives us the equations of motion of the system, mx double dot plus cx dot plus kx equal to externally applied force. We must understand that with this step we have modeled the system. Why do we say we have modeled the system? Well, the system is capable of certain motions within the boundary conditions. We'll come to that in a second. But given the boundary conditions, the system is capable of certain things. What set of mathematical equations will describe the motions that are possible in such a system? It is the equations of motion, because these motions, by Newton's first law and second law and third law, cause the movement, which in turn are caused by the external forces. Therefore, to model the system would mean to model the motion of the system. What is boundary conditions? Boundary condition is the range of independent variable typically, and the consequent state of the other variables within the system at those times. In this case, time is the independent variable. So we look at when time is 0 and time is infinity. Time can go from minus infinity to plus infinity, but there is not much sense in discussing about negative time in this case. So initial condition becomes t equal to 0. At t equal to 0, the spring mass damper system is already hanging at rest. So any static deflection in the system is already happened, and it is taken into consideration at the point at which the system now is at rest. So at t equal to 0, the deflection is defined as being 0. So the origin is at rest, taking the static deflection out of consideration. Initial velocity is also assumed to be 0. So the initial boundary conditions at t equal to 0 or x equal to 0 and x dot equal to 0. There are no final boundary conditions in this problem because we don't know what the system is going to be doing at t equal to infinity or at t equal to some time t1. Step 5, system response. System response is one thing that we are not going to get into very heavily except look at it intuitively and logically. The reason for that is once we start analyzing system response, you have finished system identification and system modeling, and you are going into system response or model analysis or system analysis. That is something that splits into short term and long term, and that is done mathematically in a later lecture. So if we apply the different kinds of loads that one will come across in real life. One is a constant load on a mechanical system where a constant force acts on it, or a constantly increasing force or a constantly decreasing force, or a cyclic load. In short, a load that is given by some equation. So these three cases are shown in the slide, and these three types will correspond to majority of the routine situations we may encounter. Solutions for a constant force is very easy. A system is hanging at rest at its static deflection point. You apply a dead weight on the system. It's going to stretch to some point and stay there. No further activity will be there. So the deflection of the system is going to be controlled almost exclusively by the spring stiffness. So the deflection will be equal to Q by K. There will be no oscillating response. There will be no free response, free oscillation in this case. Similarly, for a continuously increasing load where F is equal to Qt, where Q is a constant. As time increases, the load increases. In this case also, the deflection happens at any instant in time depending on the value of F, and it is equal to the load F divided by the spring constant K. We are not concerned with free oscillations here also. Solutions to cyclic loads such as Q sine omega t. Why do we always use sine omega t? We use sine omega t because it's a convenient model for a cyclic system. The initial condition at t equal to 0 is 0 because sine 0 is 0. And the cycle is defined by 0 to 2 pi. So when we take this model and put the external load as Q sine omega t, this differential equation has two parts to its solution. One is the homogeneous part and the other is the particular integral. The homogeneous part is achieved by solving the differential equation by setting the right hand side equal to 0, which in its turn will give you the free oscillations of the system. The particular integral is evolved by taking into consideration the forcing function. These solutions can be found in any standard textbook, and one of the best examples is Mechanical Vibration by S.S. Rao. The process of modeling, as we have done just now, starts with our identifying the applicable theory, followed by defining the problem that we want to analyze, such as identifying a car or a motorcycle or a machine, and then identifying the various components of the part, namely the inertial load, the stiffness load, the damping load, and the external load. Then we look at the boundary conditions. What is it to begin with? What is it to end with? Once you have assembled the model using any one of these two techniques or any other techniques that are possible, you look at the system model and see if the model is correct. You take into account for a particular input what is the analysis of its response. To do the analysis of response, there are many things involved. One of them is to use Laplace transform on the equations of motion to simplify the motion. It takes differential equations, reduces them to algebraic equations, which are very easy to solve. For instance, the sinusoidal load will reduce the equation to a quadratic equation, which is very easily solved. There are various methods to study the time-based response and the frequency-based response, such as Bode plot, root locus, Nyquist, and so on. We will look at all this as time goes by. But right now, you have an understanding. You see a system outside. You want it modeled on your computer. This is the fundamental way to go about it. There are many refinements to this process. That is why I have put the word iterate in the last slide. To iterate means improve the accuracy of the system that is modeled. What we have gone through so far is just a very basic process by which we will get a very basic model. Call it a first level approximation if you will. Thank you. In the last slide, there is one point I wish to draw your attention to. I have given a YouTube video which talks about a Lagrangian. Many of you by now must have wondered, what is a Lagrangian? T plus V, we all know. We know that sum of total energy is a constant in the system under ideal circumstances in Newtonian mechanics. But then what is T minus V? Does it have any physical meaning? The Lagrangian, is it a quantity which we can understand practically? Well, that's a little high level for this course, particularly since it concerns Lagrangian mechanics. I suggest you watch this YouTube video. It'll help you gain some level of understanding. Thank you again.